Good morning. It's a pleasure to speak here today. The charge of the organizers was to talk about the challenges of intensity mapping, and I'd like to begin with the challenge of definition and use that as a way to introduce the approach. In a typical galaxy survey, we would map the array, deck, and redshift of a large catalog of objects and then situate those in a three-dimensional volume. A natural question to ask is why we need to resolve 10 kiloparsec scales to learn about the universe on 10 megaparsec scales, and why we can't, in some sense, take our glasses off and learn just as much with a blurrier version of that. The way to make that work is to use line emission to make a correspondence between redshift and frequency. So these are simulations of the carbon monoxide J1 to 0 transition that were done by Tony Lee et al. And you can see that overdensities of galaxies translate into overdensities of light at a particular frequency, in this case in the tens of gigahertz. This approach, I think, had its origins in a paper by Hogan and Rees in 1979 that was stimulated by a discussion of Sunayev and Zildovich in the earlier 70s. And this paper identifies several areas that are still key to the modern approach. One is that this measures cumulative emission. So it's not just the brightest objects in a catalog, but the sum of all line emission. An intensity map survey should have narrow bands. If the bands are too broad, the density contrast will be washed out over those wide slabs of the universe. And then finally, they acknowledge that there will be bright foregrounds, but that these should be spectrally smooth compared to the structure of the signal. The next major advance, I think, was by Bevington et al. 1986 with the Cambridge 6C survey. And here they point out that you can difference adjacent frequency bands to suppress the bright structure of point sources, which you see is quite complex in that instrument. So what are some more modern motivations for pursuing intensity mapping? I think aperture is one of the main drivers here. That is, pushing to higher flux sensitivity and lower confusion also pushes to large apertures. And from my point of view at NASA, we would like to do more science with smaller apertures, given that it drives cost. So in contrast, intensity mapping is a measure of the surface brightness, like the CMB, and that means that the aperture is a sort of second-order concern, and the primary concern is the sensitivity from detector noise or photon background. Second is the point that Hogan and Rees make, that it's sensitive to the cumulative emission of all sources, so it's a blind, complete census, but it's also bad because it's sensitive to all other forms of radiation in the universe, so we have to be able to separate those. Intensity mapping allows studies of very large volumes, and that means that there's not a risk of surveying a cosmologically over or underdense patch. There are a wide range of lines to study that allow probes of multiple environments, so I'll describe that in the next slide. And this is also a fully cosmological measurement. That is, we learn about the clustering of the line emission, and the bias of that clustering tells us something about the halo hosts that contain, for example, star formation or neutral gas. And finally, there's a completely different set of systematics in intensity mapping than any other sort of survey. So this cartoon shows a rough version of the gas phases of the universe. So the IgM is ionized. Gas can become more dense and self-shield in galaxies to form neutral phases. That can cool to become molecular. That can collapse into stars, which then produce higher ionization states. Each one of these regions has different tracers that can be probed by intensity mapping. So 21 centimeter probes the neutral gas. CO is an excellent tracer of molecular gas. C2 is in multiple phases of the gas, but is a good tracer of the star formation rate. Lyman alpha emission is a direct tracer of the radiation from luminous objects. And additionally, you should also think of the cosmic infrared background as being an intensity map in that it's the integrated dust emission. Now, we can split hairs on the exact definition of the foreground brightness, but I'm going to argue that really in all these cases, the foregrounds are something like 100 times brighter than the signal we're going after. And in some cases, it might be 10 to the 5 times brighter. So it's a significant challenge for especially the instrument and its calibration and dynamic range. So the first sort of definitional challenge I'd like to address is the comment sometimes made that, well, intensity mapping is just a method. It's not directly science. So just in a historical context, every major revolution in astronomy has been through the introduction of methods. So in the period after Galileo, refracting telescopes became larger and larger, and it's a gross simplification, but in many ways the field bogged down as resolution improved, but the games people played were to detect, for example, more and more double stars. It wasn't until the introduction of spectroscopy that new horizons with redshift and composition opened up. And again, the method of spectroscopy stimulated black body measurements that arguably paved the way for quantum mechanics and the argument of the cosmic microwave background. Radio detection methods that had nothing to do with astronomy led to the detection of the CMB. So we're now in an era where CMB instruments are becoming much larger and optical instruments are becoming much larger. And the hope of the intensity mapping community is that we'll be able to do compelling science with smaller instruments, or science that's not possible any other way. So that's the promise of intensity mapping. The reality of it has been very challenging. So in the rest of the talk, I'd like to focus on some of the stumbles and lessons learned, and talk about what things we can do next. So the way to see why intensity mapping is challenging is to look simply at the sky at, say, 70 gigahertz, where you can see the CMB, versus at something relevant for 21 centimeter, which is completely swamped by galactic emission. So the basic statement here is that most of the radiation in the universe is not reprocessed by resonances. And that's what makes intensity mapping so hard. Now I'd like to connect the method to several different scientific areas that people have pursued. And I think a good way of thinking about the structure of this is sort of like this grass, that early on the impetus was early structure and reionization, and the idea that flux sensitivity is expensive. But, and that's led to a manifestation of a number of experiments that are now placing very good upper bounds on reionization. But that led to some agitation that, well, we're a decade or more out from a detection of the anisotropy from reionization, so what can we do even sooner that's still interesting? And then there's a suggestion of dark energy and FNL, large-scale structure surveys, and the idea that intensity mapping is potentially a much less expensive way to do a redshift survey. And that's led to a number of experiments that are also observing now. But again, there's some agitation that, well, we're a decade out from detecting the BAO, so can we do something even sooner? And here the impetus was galaxy evolution, and that led to a number of searches that have produced detections. This is the area I'll talk most about. This is my best effort at compiling the list of all ongoing and near-term intensity mapping experiments. They're surely incorrect, or some things will be absent, so if you see anything, please tell me. But the main thing to take away here is that there are a large number of experiments going after reionization and 21 centimeter at low redshift, but also C2, CO, and optical transitions. And these all pursue a wide range of redshifts and instrumentation approaches. Another way of plotting this is in redshift and survey resolution or area. And this is just for a subset of those experiments. And you can see that they have an ambitious plan to map wide swaths of the universe. I'd like to briefly comment on two NASA missions that were recently accepted for intensity mapping. Starfire is a 2-meter warm telescope with heritage from BLAST that uses an EMKID coupled to a grating spectrometer, EMKID array. And it will focus on C2 from redshift of 0.5 to 1.5, so the peak of the star formation rate. And this is led by Joaquin Vieira at UIUC in collaboration with a number of US universities. Exclaim is a 0.75 meter cryogenic telescope, so more like something that would fly in space, and uses an on-chip phononic EMKID spectrometer to study CO at lower redshift and C2 at higher redshift. So these are, I think, nicely complementary, and that will be very interesting to follow. So we look at a data cube of an intensity map. Well, the first term to think about is the thermal noise of the instrument, and that's uncorrelated in space and frequency. The next is galactic emission, which is spatially smooth and spectrally smooth, but very bright. extragalactic emission, which may have a lot of spatial structure but is spectrally smooth, and radio frequency interference, which can change spatially, spectrally, and even temporally. And then one of the main challenges, I think, will be the instrumental response to those foregrounds. So from the previous table, you could see that there's really a range of experiments that are being pursued now. For this talk, I'd like to have a sort of unified way of talking about the analysis of the data from those experiments and some of the challenges. I think a good way of doing that is through a quadratic estimator. And the idea here is that these experiments are going after two-point functions of the field. So these are the amplitudes P of the covariance of the data. And that data could be RA-DEC and frequency or visibilities or even time-ordered data. And then that has some additional noise covariance N. So you can ask what the optimal estimator of those P alphas is in terms of a quadratic combination of the data. And that's shown as the next expression. And the form of the optimal quadratic estimator is this Q. It looks somewhat complex, but what's going on here is there's a normalization in the denominator, and then in the numerator, what's going on is that each C inverse applies to the data on both sides. So your noise inverse weighting the data and dotting it against the covariance structure you care about. So the broadest categories of analysis that the experiments are pursuing, I think, could be described by a priori, which is somehow that the covariance is known in advance of the analysis, or empirical, which is what it's sort of come to be called, but you could also call it blind, and that's that the covariance is partly determined from the data itself. The other broad class of analysis is an autopower, that is when both sides of the quadratic are intensity maps, versus a cross power when one side is intensity, the other side is a galaxy survey. So now if we look at the covariance, this is a key part of the estimator. This is a very large matrix, so it might be 10 to the 6 by 10 to the 6. And one question is how we even handle that in software, but a bigger technical challenge I would raise is that is the question of how we know 10 to the 6 by 10 to the 6 numbers with the sufficient precision that we need to do the analysis. So if we look at what's in that matrix, well, there's thermal noise. That can be known reasonably well through instrument characterization. And you can actually avoid that in the estimator by cross-correlating subseasons. There's continuum emission, which is likely quite spectrally simple and arguably known pretty well in advance. But then the real challenge, I think, is in the instrument response. And this may be known in some generality, say passband structure or beam, but it may not be known specifically well enough to form the covariance to do the analysis. So if we look at what happens if the covariance is known imperfectly, well, on the one hand, in this estimator, it just departs from optimality. So long as we have a best effort at estimating the covariance, that's not a big issue. I think the big challenge here is in the bias that you have to subtract off, which depends on a model of the covariance. So if that model is incorrect, you can have additive bias, for example, to the power spectrum. Next, if the covariance has terms that are estimated from the data itself, I'll say more about what I mean by this later, but it adds some level of subjectivity and nonlinearity. So nonlinearity in the sense that C inverse times X is no longer linear in X if C itself depends on the data. So that's all relatively abstract. I'd like to talk about that in terms of some real data. These are now somewhat old, but I think show some of the basic challenges quite well. So this is data we took with the GBT in 300 hours of observing. This first graph is to calibrate you to the level of the signal that we expect. And you can see that the RMS is around 0.1 millikelvin when smoothed by the GBT beam. And I'm going to animate this. You can see that each frequency slice is dramatically different from the previous. Another way of saying that is the signal has essentially full rank. And if we now plot the real GBT data cube, first of all, you see that the color bar is 1,000 times larger. Okay, so there's significant contamination. And there's very little happening in the map. You see some thermal noise where the survey depth is lower, and bands that drop out from RFI. But what you really see here is the galactic emission as a gradient, and then bright extragalactic radio sources. So this gives you some sense of the challenge that these experiments have. So the first question we can ask with this data is, are the foregrounds spectrally smooth? And to do that, we can find the eigenvectors and the eigenvalue spectrum. And the dashed line is the eigenvalue spectrum for just thermal noise. And you can see that the measured spectrum has quite a number of modes in excess of that, especially the single brightest mode, but there's also a tail that is problematic of dimmer modes. If we now look at the eigenvectors of those, they're rank ordered with the brightest on the top. The top one is roughly the average synchrotron emission as observed by the instrument. And it's not a nice power law in this case because we observe a source out of the field at a different time and then move back into the field. So this relies both on the calibration in this wide band and on the stability, the transfer of that calibration. The next is the chromatic beam response. And this you can actually treat in the analysis, but I've left it in here just as an example. The one following that is polarization to temperature leakage and its particular spectral pattern. So you can see that none of these are smooth, and that really the whole story that's happening here is about the hardware. So what you want to do is control all of these terms in the hardware in advance. So the statement that the foregrounds are smooth can be given a little bit more nuance by saying that the foregrounds, as observed by the instrument, need to have fewer degrees of freedom than the signal if we want to be able to dig the signal out. So what we did in the GBT analysis was to write the covariance separably as a spatial RA deck weight, the C inverse there, and a frequency projection, the pi matrix shown below. So what this does is it projects out the eigenvectors that I just showed from each line of sight. So in this case, the spectral part of the covariance is determined completely from the data itself. So this is the map after removing 25 modes, and you can see that it's getting closer to the sort of 0.1 millikelvin regime, especially in the deeper part of the survey. The outside part has quite a bit of thermal noise. So this shows that the approach is promising, and with that, we are able to achieve a good detection of the cross power and an auto power that still shows some signs of additive bias from residual foregrounds. Wigglesy. Yeah, I'd be happy to say more about this. I'd like to focus on the methods, but I can put this back up in questions. So we can do a sort of thought experiment to ask how much signal is lost in this weighting or projection process. And if we say that there are 256 channels that are full rank in the signal, and we remove 25 random modes, you could sort of intuit that there will be 90% of the variance of the signal remaining. But the assumption there is that the modes that we project out are uncorrelated with the signal. But if we determine the modes from the data itself, they must be correlated with the signal. So we can do another thought experiment here to say that we have a survey with 3 spectra. And if we find the eigenvectors of that system, there are 3 eigenvectors. If we project out those 3 eigenvectors, we're left with identically 0 signal, even though there might be 256 bins. So after the matrix algebra for this is a mess, but it does result in a fairly simple expression for the signal loss. And this shows that there is the frequency domain part, that the number of modes over the number of frequency elements, but it's also multiplied by the number of modes you project out divided by the number of angular resolution elements, which in this case is 3. So this is a key part of intensity mapping data analyses, and there have been a couple of approaches in literature for handling this signal loss. So in the original GBT work, we used a transfer function, and the idea here is to measure the output of simulated power relative to the input. That's a simple ratio, and that's shown in the top there. So it's anisotropic. The right is actually the beam transfer function rolling it off, but then the left is the foreground cleaning. Zhang et al. With Ben published a very nice method which jointly determines the contamination modes and the signal variance. So this transfer function is accounted for self-consistently, and that's shown in the lower plot. And then last week, Karina Chang and the paper collaboration published a very nice Bayesian approach for handling this, where they estimate these simulations to estimate the output, what you would measure from simulation, then flip that around to infer from the real data what the true power is. And this acknowledges the stochastic aspect of the signal loss. That is, for a given signal realization, there'll be a unique amount of signal loss. So if we look at how this has been applied in a couple experiments, let's start with GMRT. GMRT had an upper bound of 70 millikelvin in 2011, and as we started to find these challenges with the GBT analysis, they revisited GMRT with an account of signal loss and revised the upper bound to 248 millikelvin. So a pretty significant upward revision when accounting for that. In the recent paper from the paper collaboration, they consider an upper bound from Ali et al. 2015, shown in the dashed line, and that after accounting for the signal loss in that case, the bound moves almost a factor of 10 to the 5 up. So there's a significant degree of signal loss there that needed to be accounted for. So what they went for in the end was a simpler thermal noise weight that could be known a priori rather than determined from the data. And that's shown in the black point. So you can see it's a lot better, but still higher than the original upper bound. There's not an analogous study of C2 or CO intensity mapping yet, but this is simulation work that I did for a study of PIXI, a proposed NASA mission, cross BOSS for C2. And what I want to draw your attention to is the upper dashed line, and it being something like a factor of 10 higher than the black line, which is the thermal noise limit. And the upper line is when you have 0.4% spectral gain variations. So this shows that this shows the sort of degree of instrumental control you'd like to have to be able to clean the foregrounds from these data. So one thing that I think is very compelling in the submillimeter region is the ability to calibrate the instruments quite well. So what you can use there is something that similar to what was used in FIRAS, where if you have a conical structure, a single bounce off of that structure might be 90% black, but the set of rays going into the cone may bounce 7 times, so the structure appears to be black to a part in 10 to the 7. So that allows calibration of these instruments to a very high degree, which probably isn't possible in the radio regime, just because of the size and temperature of the calibrators you would need. So I want to come back to the idea of, or the challenge of the subjectivity of the cleaning. So if the covariance isn't known, that means there's some aspects of it that might have a free parameter. So as you make that parameter larger, that mode, that contaminated mode, gets deweighted more and more. So I'll call that the aggressiveness of the cleaning. Likewise, if you don't know the total number of contaminated modes, as you add more of them, again, the sort of aggressiveness of the cleaning. So there's this sort of subjective direction of the covariance. Now, for the cross power with the galaxy survey, there's no additive bias to uncorrelated foregrounds. So as you make the cleaning more aggressive, you remove more foreground and improve the cross power, but then at some point, you start removing more signal, and then the errors increase. So there's a clear optimum cross power in this space of the cleaning. Now, in the case of the auto power, the additive bias will just continue to drop as the cleaning becomes more aggressive, or as you deweight more modes. And at no point on there is there an auto power that I would be willing to claim is a detection, because at any point on there you could say, well, there's probably some residual additive bias of foregrounds. But what there is a least upper bound. So in this space of cleaning, there is a bound which is best, and that defines the best covariance matrix to use. So I think an important question that still needs to be addressed is when we're willing to declare an upper bound, when we're willing to declare a detection of an autopower. And you might argue that one way you would do that is if the cleaning reaches a sort of plateau. So instead of continuing to drop, you could maybe argue that the cleaning has removed all of the foreground, and now you're in a regime where there's only signal, and then the signal starts to get lost and the errors increase. But even with that, you could maybe argue that what this is actually a plateau of contaminated modes that are just very difficult to deal with. So I think this is an interesting challenge for the autopower. So what would it take to be in this regime for an experiment to get this plateau? Well, you'd like the number of bright foreground modes as observed by the instrument to be much less than the number of signal modes, so that you can clean those bright modes and end up with some signal remaining. Now, for experiments like CHIME that are going after a feature in the power spectrum, that may also be much more robust to an additive bias. So you might be able to see the BAO even if there's some big offset in the data. So I think the main summary with this challenge is when we're willing to declare detection. And this is similar, I think, in many ways to B modes. So I've talked about the 2-point, but you may also look at higher point information and whether those can be made robust to residuals. So the gold standard for intensity mapping is corroboration through cross-correlation. And I'd like to talk about a challenge that appears even there, and that is that usually with intensity mapping, one thinks of an isolated line, but the spectrum of these galaxies is really quite a bit more complex. So it's not just a single CO line. There's also a thermal dust spectrum and a synchrotron spectrum. And in the near IR, it's quite a bit more complex. So what that means is that for a given redshift, not only do you get cross-correlation at a given frequency, but those same galaxies emit continuum radiation that correlates with another set of frequencies. And I think this was first shown in data in Sarah et al. 2014, where they look at Sloan LRGs cross with Planck and find a strong cross-correlation in all the channels. So this isn't related to any line emission. This is really measuring the SED of the galaxies in the BOSS LRG redshift slice. Anthony Pullen extended this analysis by adding a free parameter which describes C2 emission that's consistent with being at redshift of 2 to 3.2. And he finds marginal evidence for that in excess of this correlated continuum, but not willing to claim that as a strong detection. So if you look at what this sort of challenge of scales here is, this is the Planck 545 in the BOSS North region. You can see that the galactic foreground is still quite bright, and that's shown as the upper black line. So about a factor of 10 below that is the correlated CEB. So this is really quite a bright signal. And then a factor of 10 below that is the C2 as it appears in this slice, at the level in Anthony's paper. So this shows the degree of challenge of both the uncorrelated and the correlated foregrounds. So an experiment needs to be able to suppress the uncorrelated emission from the galaxy, but also to marginalize over the correlated continuum emission from the sources themselves. And then on top of that, to be able to actually measure the signal of interest. So in practice, to do that well, you need something like 10 bands. So there simply aren't enough degrees of freedom to get a slam dunk detection with Planck alone. But the good news is that most future intensity mapping experiments will have hundreds of bands to allow those degrees of freedom. So this is an example of Pixie as a spectrometer with the upper lines are the correlated continuum emission going up, and then there's a blip from the C2 emission. So if you think of that as sort of a baseline subtraction, you can take out the dust continuum and see this C2 feature. So an additional challenge to cross-correlation comes when you select the redshift sample from the intensity survey itself. So Rupert Croft et al. Have two very nice papers on Lyman alpha intensity mapping with BOSS, where they talk about some of the challenges here. So they look at the cross-correlation between quasars measured in BOSS with other fibers where the galaxies have been removed, and they're just looking at the diffuse light. And they point out that adjacent BOSS fibers can be contaminated. So the quasar is on the red channel there. So some contamination leaks through to adjacent frequency channels. And what that means is that, in the first analysis, they threw out correlation pairs that were in fibers near the quasar, but include all other fibers. Now, in the follow-on 2018 paper, they point out a sort of second-order effect where the fiber around, so this fiber that's indicated there is contaminated by the purple quasar, and that quasar is spatially clustered with the yellow one. So there's clustering in that fiber with the quasar, the target one, which is independent of any actual Lyman alpha emission on the sky. So in the follow-on, they throw out any fiber. Well, there are multiple approaches, but the simplest is to throw out any fiber which is near a quasar. And this throws out this sort of second-order effect. So in this case, the cross power was reduced by about 50%, accounting for this sort of anomalous term. So in the last section here, I'd like to talk about a couple of interpretation tricks that may stimulate other ideas for intensity mapping surveys. And the first is sandwiching. And the idea here is that the cross power is really a lower bound on the line intensity because of the stochasticity between the two tracers. They're not perfect tracers of each other. And the auto power is an upper bound because of additive bias of residual foregrounds. But what you can still form is a sort of Bayesian sandwich of the upper and lower bounds to bound the true emission between the two. So this suggests doing a survey that contains both of those elements if an auto power is not possible. The next is a multi-tracer approach. And the idea here is that if you think about the covariance between an intensity map and a galaxy survey that's shown in this sigma matrix, if the quantity of interest is the power spectrum, the error on the determination of the power spectrum is shown in the second equation down. And that has a cosmic variance term as well as a noise term. And so that's familiar from say, a CMB case. But if what's of interest is not the power spectrum, but the line brightness, that's the alpha, that alpha can be determined without cosmic variance in an approach similar to what's been pointed out in large-scale structure surveys. And that instead just depends on the noise in the survey and the RMS of the fluctuations. So I think another interesting question is whether this sort of multi-tracer approach can suggest new types of intensity surveys, either potentially on smaller areas. Additionally, with cross power in the shot noise regime, there's a clear way to separate emission into different classes of hosts. And Laura Volz has a nice paper describing that. Okay, so finally, this has all really been related to the 2-point functions and how we get to the power spectrum. But then there are a number of questions of how to interpret the power spectra once we have them. So on the one hand, the 2-point function, the two halo term is in a linear regime and easier to interpret. And then on the very small scales, the shot noise and its correlations are fairly easy to interpret. But I think an open question is how well we can do with one halo information. And this has been challenging in CEB analyses. So that's an open area, I think, probably for interesting simulation studies. The next is how we connect intensity mapping studies of line brightness with other studies of galaxy evolution and things like semi-analytic models for galaxies. And related to that is, in connecting to studies of galaxy evolution, is how we connect intensity mapping to studies of discrete sources. And there's been quite a bit of nice work done on this already that I cite here on the right. And this combines intensity maps with Lyman alpha studies and discrete H1 emission in observations like alfalfa. Related to the power spectra on linear scales, what we're measuring is the bias times the brightness, whereas each one of those is independently interesting. So another, I think, question that needs to be addressed is how we could maybe hope to separate bias and brightness. So bias tells you about the halo hosts of the emission, and the brightness is the gas in those systems. Additionally, does a multi-tracer approach suggest new types of surveys? And then a really broad class of questions of how one can rule out interlopers in the autopower. So this is yet another, I think, challenge of the autopower. So I think the principal challenge in intensity mapping is to combine the instrument design and analysis to be able to make a clear detection of an autopower. And a question there is, what criteria and procedures can we have to build confidence in the autopower? So I think one thing that could be interesting is an ability to weigh multiple interpretations, so to say that it's more likely to be autopower from real signal than it is to be a particular instrumental systematic. And then even for the cross-correlation, where we're seeing the redshifted signal, there's still a question of marginalizing over the correlated continuum. And I think an interesting statistical question there is the validation of the model. How do we know that we're marginalizing over the right model for the correlated emission? So the focus here has been on the challenges of intensity mapping, but I hope I've also been able to convey some of the excitement of the approach and the fact that these are mainly technical and also interesting challenges. That is that by chipping away at instrument design and data analysis, we hope to be able to fulfill this promise of intensity mapping as a new astronomical method. Thank you.